Okay, Giancoli 7-1. We're going to start talking about momentum. So momentum and its relation to force. Momentum is a vector, and we use P. Obviously, M's used for a lot of different things, so that we use P for momentum. I had a professor call it momentum, which kind of helps me remember P. But momentum is equal to mass times velocity, okay? So the rate of change is momentum is equal to the net force. So net force is change in momentum over change in time. So this is also using Newton's second law. So momentum is mass times velocity. Change in force, okay, or net force is equal to change in momentum over change in time. So let's use those equations and do some solving. Force of a tennis serve. For a top player, a tennis ball may leave the racket at a serve at a speed of 55 meters per second. If the ball has a mass of 0.060 kilograms and is in contact with the racket for about 4 milliseconds, we want to estimate the average force in the ball. Would this force be large enough to lift a 60-kilogram person? A lot of stuff going on there. Do it now.
Okay, so tennis ball's leaving a racket with the speed of 55 meters per second. If the mass of the ball is 0.06 kilograms and the contact is about 4 milliseconds, we want to determine the average force on the ball. And would the force be large enough to lift the 60-kilogram person? Well, average force, change in momentum over change in time, and that's final momentum. I guess I shouldn't put M, should I? I should put P. It's my fault. Final momentum minus initial momentum over change in time. So let's look at momentum final. It's leaving with the speed of 55. So if it's leaving with the speed of 55, I got to say that the mass times 55 is my final. Since it's not moving initially, it's going to be 0, right? And then my change in time, and it says 4 milliseconds. So I got to convert that to seconds. So it's 4 times 10 to the negative 3 seconds. Let's move the decimal 3 to the left. And now I can find my force, my average force. 0.06 times 55 divided by 4 to the negative third. And the average force, 825 newtons. Now, if our average force is 825 newtons, we want to know if that's going to be the same as lifting a 60-kilogram person. Well, a 60-kilogram person has got to beat the force of gravity. So I take 60 times 9.8. And when I do that, I get 588. So that's the force required to lift this person. That force is greater. So it's greater than the force to lift that person. So yeah, that force could do it.
7-2, washing a car, momentum change in force. Water leaves a hose at a rate of 1.5 kilograms per second with a speed of 20 meters per second and is aimed at the side of the car, which stops it. That is, we ignore any splashing back, okay? What is the force exerted by the water on the car? Do it now.
All right, so first off, we want to use this equation again. We know that it has an initial velocity, but when it hits the car, it has no velocity. So therefore, it's not going to be a final. So my final, right, my force, my final is going to be 0. So now I want to find the initial. Now this thing of 1.5 kilograms per second is the way the water's coming out of the hose. We're going to assume that time change is going to be 1 second during this whole process. So our mass is going to be 1.5. And then we multiply it by our velocity during that 1 second, which is a constant velocity, so it doesn't matter, 20 meters per second. And we're going to divide that by our change in time, which in this case we have already said is going to be 1 second, because that's what we want it to be. Now, if we made it 2 seconds, this would be 3 and that would be 2. If it was 3 seconds, this would be 4.5, this would be 3. It doesn't matter. We just chose 1 as our change in time. So now I take 1.5 times 20, take 0 minus that, divided by 1. I get a force of negative 30 newtons. So that's the force, and so that's the force pushing back. So like it's going this way to hit the car, and then the force going backwards is -30. So that's what we got. We got -30 Newton force going backward.